So guys, I want to touch this DC power supply. Let me move it down. This DC power supply. Okay, so the main process is trying to convert from AC to DC. AC is in form of like, let's say it is not straight, like this kind of, like it is not straight, something like this. If you can see it is not straight. Let me zoom it. You see it is not straight. Now you are trying to convert this to this one, something that is like a straight stuff. Now you like, let's say you are using a wire now, then the wire is like somehow like scattered. If you straight it by like straightening it in this process, let's say as you are straightening it, right, you're actually like cutting out something so it will be like straight and like accurate. That means the wire is going to like reduce, right? That means if you're having, it's just showing that if you're having bigger like voltage in AC, you'll be like, for the DC it will be small. That is why you have this transformer here. This transformer, look at its job is to step. Okay, so the rectifier, now we are going to be dealing with the rectifier. I want to touch the calculation under the rectifier first. There is under the filter the voltage regulator. Now you know that, like, now when this AC, now when it passes through this transformer, the rectifier, then the filter, it's like straight, but the filter makes it more like shorter. Like when it makes it shorter, now the voltage regulator now will now make it like trying to like, let's say it's trying to like withstand the pressure, like it's trying to like make it like straighter, like something like, and longer, something like that. But no matter how long it's going to be, it will not be the same like length with AC. I'm just trying to just put it in the kind of this thing. So meaning the VDC now can never be what bigger than the AC. Now, okay, let me touch something now. I think I just explained this, like the whole process is trying to change this to this when you are following this process. So now, let's go down. Now you see this one now. This is a single phase half wave rectifier. Okay, let me just call it a rectifier. Now for a rectifier now, please look at this carefully. You only have one diode, right? Now see, I'm going to do something now. Let me try to let me rest a little bit. Now I'm going to do something now. Now look at this. You have RL, right? I'm going to show you the meaning of all of this and this thing. So okay, let's screenshot this. Should not screenshot this, something like, can I screenshot it? Okay, I can screenshot it. Okay, there's a reason why I'm trying to do this. Let me go back to my, okay, so now I think I can bring this down. Exactly, this is what I'm trying to do. Okay, see now. Okay, let's say you have something like this now. Let me zoom in. Now these are the average and RMS value for this textbook. Let me put it from down. Now for this textbook, these are the value. I want to explain it in a kind of way that you're going to understand it. Some of you guys might be using a different meaning, like I saw some people using VIP. You see the same thing, but just different textbook. So okay, let's say, look at this VSM here. VSM say that maximum value of transformer secondary voltage. Now the maximum VSM, like how will I put it now? This VSM here is the maximum value of transformer secondary voltage. Now you have for primary voltage, you have for secondary voltage. Now the RMS of the primary voltage is always somewhere around here, right? So when it's now like during the okay, let me just continue from here. Okay, this VS RMS value of the secondary voltage, VLM the maximum value of the load voltage. Now look at, if you have primary voltage here, and let's say you are given you know those 5:1, 10:1 that they used to give you guys, like that used to be here, which most times is always for all this center type stuff. Okay, so you are going to convert it to what? Now this VRMS, you are going to convert it, like, and using that 10:1, you convert it to VRMS for secondary. You know, it's ready for primary. Now, like, let's say you have 230, because mostly it's always 230. Let's say you have 230 for the primary now, as the VRMS. It's always the VRMS that's here. Now, divided by, let's say you have 5:1, divided by what? N2 over N1, which is simple as what? 1 over 5. Okay, sorry, multiply by 1 over 5, which is the same thing as divided by 5. Now, when you divide it by 5, now it will give you something. That thing it give you is the VRMS for the secondary. Now, when you get the secondary on now, you're not going to multiply it by root 2, by square root of 2, to now get the what? The maximum value of load voltage. Now, look at this one here now. The maximum value of load voltage is equals to what? This VSM mean what? Look at what they write here. Now it means maximum value of transformer secondary voltage. The then you see VSM. Then you see VSM minus the minus diode drop minus secondary resistance drop. Now this diode drop and secondary resistance drop all means, like, if let's say is silicon. Now silicon is 0.7, right? Now you're going to and remember, for half wave you only have what? You only have one diode, so it will be what? Minus 0.7. Most times they don't need to give this secondary resistance drop. Like, most times it's always like, and sometimes that is if you are asked to what, like, if they give you the diode is silicon, then you are going to what? After you have get the VSM, by multiplying the what? Root 2 times the secondary VRMS, which you got from what? That primary VRMS, by dividing it by the what? By the N1 over N2 over N1. Now after you got that one, now then you now minus the answer. What it now give you is now your what? The maximum value of load current. Now after that one, now okay, let's continue from there. Now VL now is your RMS value of load current. That means what I'm trying to just tell you here is what? RMS value of load current, meaning what? It's just the it's just the RMS value of load current, the secondary RMS value. You know, the primary RMS value will be given maybe like 230 volts, I don't yeah, something like that. So once you now convert it to VRMS secondary, it will now be what? It will now be the RMS value of load current, because most times we are dealing with secondary. So far, I feel like that primary is just like they just give you so you can try to get the secondary and continue like that. Now the RMS value of load current. Now remember, now this VRMS, you are going to multiply it by root 2, right, to get your what? VSM. Now remember that VSM, you will not subtract the diode drop. That is if you are told that it is silicon, sometimes it can be germanium, but most times it's always silicon. It's rare for me to see something like germanium. So from there now, you now have From there now you now have your IL, the RMS value of load current, that is IRMS. Remember, IAC is the same thing as IRMS. In most textbook I've actually like check, they don't used to use IAC, but they used to use IDC as IDC. I'm just telling you now so it will be easier. IAC is the same thing as IRMS. So you will see some textbooks saying like now if they're calculating for PAC, instead of they should use IAC squared times RL, right? They will now be using, so it times RL and the either RS or then they will now be using what IRMS square times RL, meaning what the IRMS is the what is the IAC, but for the IDC you is like it is normal. Like I don't know if I can actually write here for the IAC. No, it doesn't. And I don't want to like start writing all these things already night. That's why you guys are not going to see it clearly. I feel like this is the best way you can see it. So okay. Now the next one is average value of load voltage. When they say average value of load voltage, when you ask to calculate average value of load voltage, they are simply asking to calculate what VDC. It's like telling you, okay, after everything, what do you now get? Say you grab like after you have changed like the scattered wire, after you now change everything, what do you now get? Then you now say, okay, this is what I got as my VDC. Now IDC, for the current, average value of is same thing as the IDC. Now ILM, the maximum value of load current, which is the same thing as what IM. IM will be can be gotten from what? From as we are going down, you will see the calculations down here, so that as I'm talking you're going to understand what I'm saying. So the load resistance, you guys know that one. The transformer secondary resistance, sometimes it can be given, sometimes it cannot be given. Most times the load resistance like is always given. How the diode forward resistance. Now there is something I want to tell you now. Let's say you are dealing with full wave bridge which has 4 diodes. If you have to calculate anything, like if you're looking for IM there, IM, you know, is IM equals to VM over RL plus RS. Now you are dealing with 2 diodes that are conducting with, they are in series with RL, so it will be 2 RS plus RS. Now say if they give you RS as 2 ohm, you are going to add 2 ohm plus 2 ohm then plus RL because they are in series. Then you now do your IM equals to VM, then over that you are going to get your IM. Remember, VM can be gotten from where? Your secondary, from your secondary RMS. That way you are going to multiply it by root 2. So now you know IRMS is the same thing as what? IM over what? Pi. IM over pi. Sorry. Is IDC. That is the same thing as what? IM over pi. Now, for you to even understand it better now, for IRMS is what? Divided by what? 2. It's divided by 2. Why? Because when you divide it by 2 is bigger than when you divide IM by pi. Pi is 3 point something, meaning when you divide it by pi you have smaller voltage, meaning that's will be the VDC. So that in case you should not cram, like that should be the easy, like very simple way to like understand it. Okay, let me just continue from here. Okay, for me now, because me in my own book I'm using IM, here they are using ILM. So if you know it your own way, you don't have to like be scared of any this thing. So now let's say you see why they put this minus VB. Some of you can do mistake again. The minus VB is just the what? The silicon stuff. Anything it's supposed to just be VSM, which is something as VM, that from my own stuff. So let's say ILM, which is something as IM, equals to VSM, which is something as VM over. Remember, when I told you that when you're calculating for IM, both in center tap, in full bridge, in half wave, is always this format. IM equals to VM over all the resistance, RL, RS, RD, RF, any R something they give you. You're going to add everything, then get your IM. Remember, you have got you can get your VSM from your what? From your RMS voltage for the secondary. That means you are going to multiply it by root 2. So let's continue from there now. So now from here now, I'm coming. Let me check something. I want to go through my notes. I want to check something. Okay. So now, okay, let's continue from here now. Okay, I think I've explained this part. I just finished explaining it. So let's go to this part here. This part here is just showing you that what the VM is the same thing as IM times RL. The VM is the same thing as IM times RL. Meaning what? If the RS plus RD are 0, it will be times RL. If they are not 0, it will be times what? RL times RS times IM times into brackets RL plus RF plus RD plus RM thing to get your VLM. So okay, let's continue from here. VDC now. Me, I used to call it VDC. I was going to call it VLDC. Okay, but let me just in my own way. Okay, let me use voice here. So now, so you guys are going to use the same method. VLDC equals to VM over pi. Now, what I just explained now. If you use pi to divide something, you have smaller value than when you use 2 to divide it. What's wrong? Down. Okay, it's like multi this thing as close. My phone is I own my data and stuff. Okay, let me continue from here now. So it's like you are using okay, do I need to even show this one? I can just continue from here. So it's like you are using, so when I break the video, I'm going to try and see what I can do with my phone. So when you divide it by pi, that's for the IDC. Now you are still using that same VLM to find your VRMS. Remember that VRMS is something as like saying VAC, which is something as VLAC. Now you already have what? Now you already have what? VLDC. Now to find the VAC, which I told you that is always bigger than the DC, you can now what? Divide it by what? By root 2. This is for the half wave. If it's for the full wave, it will be divided by what? Root 2. For half wave, you are dividing by 2. But when you are changing, okay, let me continue from here. Sorry, for the for the VAC, you are dividing VM by root 2. It's for the IM that you are dividing by 2. It's the IM you are dividing by 2. Okay, now from here now, it's like if it gets to like 30, I will just stop. I will stop it, then we start another video. Wait, okay. So now you have IL equals to ILM is mistake here over 2. That now you know when I was telling you that you are going to divide it by 2 when I'm looking for the what? IRMS. Remember in this thing, IL is something as RMS, which I'm telling you that RMS you are going to divide it by what? 2. But for the full center tap or full or full bridge is what? Divided by root 2. The only difference between the center tap full bridge and the bridge full bridge, you have center tap and the bridge and the full wave bridge is the peak inverse voltage. I'm going to touch. I'm going to get there. So now you're going to get this one. Okay, let's continue. Now normal DC from your, like, even without cramming, when AC is bigger than DC, meaning what? And efficiency must not be more than what? 100. It means what is the AC that will be down, so this will be up. So meaning if the biggest is down, it can never be more than 100. It can be 99, it can be 90, anything, but it can never be more than 100. Before you see it to be 100, meaning there is no any actually like a resistor, like a resistance in this time, which is not possible. I don't think it's like 100, something like that. They even okay. Let's continue from here. So now remember. Okay, I think after this part, I'm going to stop first. I should just. I'm going to stop after this part first, so I can just send this one. I can save this one up first. So now PDC equals to ILDC. I don't know why they are using ILDC, but they just say IDC square. You see now, this is what I'm trying to show you guys now. You see IDC here, they still use IDC here. Can you see? That's how I'm trying to tell you that if you understand this, there's no need to actually like using different textbook. I feel like I've gone through all the textbooks, but I feel like this is the textbook that is the best. So now you're multiplying. Now there's something I want to tell you. Now let me scroll up. There's something I want to tell you. There's something I want to tell you. I'm going to scroll down back. Now, when you are dealing. Now, sorry. When you are dealing with this part here, you are dealing with all the resistor. But when you are dealing with this part here, you are dealing with just RL. Please remember this thing. You are dealing with just RL. So let's go down. Remember DC just RL. When you are dealing with AC, all the resistor, AC is something as what? RMS. When calculating it. Now from here now, you have ILDC. This is something as IDC square RL. Remember, because of DC, you only use RL. Did not add what? Look at this. They did not add this one. This is for what? This is for when they are calculating what? For the PAC. But them they use P in. You should know that PAC is one that is coming in. But them they use P in. That's why if you understand this thing, you don't need to like start cramming. I'm just trying to just break the elementary this thing so you can understand it. I'm going to, if there is time, I'm going to touch the BJT, the JFET, the special diode. That special diode is somehow I'm trying to get it very well. So now okay, so now for the IDC, I tell you before that IDC is something as what? IM over what? Pi. Because of what is smaller, and when you divide by pi, that pi is 3, you have something small. When you divide that same IM by 2, you have something that is bigger than that IDC. That means you are having what? That means this IL now, here they are writing ILDC. You intentionally, like, let me say, don't put this in your stuff or in your this thing. Use what the man uses. I think the man is using IRMS, the man in class. So don't put this IL, use IRMS. Just understand it. So when you use this IRMS now, when you are now adding it, that means you are adding it. Then they are saying that when RS, RF are 0, that's when you have R is 0 here. But when you see now, I told you that when you are dealing with the AC, you are dealing with all the resistor. That's it. They actually like multiplied by all the resistor here. But for this one, they only multiplied by what? By the RL. This one, they are multiplied by the what? Addition of all the resistor. Even if there are 10,000 resistor, you must add everything to get your PAC. That's why the PAC will be very big than the PDC. Now for the IM, now I just explained this one. Then now then they just did like the maximum, because they just did like when the R zero is one, like they're just doing the maximum. So now say if R zero is neglected, if it's neglected, meaning if it's not neglected, the efficiency will be what? Greater than this thing. If R0 is neglected, H equals to 40.6. Obviously, it is the maximum possible efficiency of a half wave rectifier. Now, this 25, let's get 26. So now I've touched the like basic file for the half wave. Then you have for the full wave. Or let me see this part here. This part here, there is a whole lot of explanation here, which I want to first touch the full bridge for the center tap and the normal bridge. And so if like a full wave for the center tap and the normal bridge and the full bridge. What am I saying? Let me see, where is it? I'm going to touch all these calculations, so they are very easy. Or with this stuff I just explained, that you can actually like go and like try it out. Now if you look at it now, this is for what? This is for full bridge. Full bridge is the one that has what? 4 diodes. This is for what? Center tap bridge is one that have what? 2 diodes, right? Now this is the diagram store, the diagram for the full bridge, the like on like the waveform. Let me put it that way. Now you know there's this thing in PQ that they say, what is oscillator? Oscillator are the ones that it produces wave AC waveform. Wait, I'll check that one later. So now let me see, is there, now you see there is no much difference. I want to just tell you I want to just break down this now. Now for the RMS, and now for the half wave is just what? From the word half, meaning what? They divided the full wave by 2. So now if you are dealing with when you see those IDC equals to IM over pi, when you now do it, you now multiply it by 2, then you have your what? IDC for what? For the full wave. For the center tap and the full bridge, I have the same calculation. For the like look at it here, something like this. Now you see it now, IDC in that half wave is IM over pi, but this one to multiply it by 2 because it is what? Full, not half. I'm just okay, I'm trying to look at more this thing. These are the normal calculation. If there is time, I'll touch it. You see, from the look, you know this center tap stuff. This is what primary VRMS. You are going to now divide this one by this 220 by 2 to get your secondary VRMS. You now multiply that secondary VRMS times root 2 to now get your what? VM. Let's call it VSM, but let's call it VM because this thing. Now VM minus, if they not talk about that is silicon or anything, they talk about is silicon. No, that means you are going to just use it straight. Look at it here. You have now look at them. Then like you see, I was saying 220 divided by 2, they multiply by root 2. You can see the same thing as 220 multiplied by root 2, then divided by 2. It will still give you 156 as the what? VM. Now this VGN, don't just use the one you know. Use the one you know. Now it's 0 to 30. Okay, this is like I'm solving one question. I'll solve a question on that video. Let me see. I'll solve question on that video. Let me explain for this full wave. The difference between the full wave and the and the half. Let me say one thing. The frequency in half from AC is the same frequency in DC, but the frequency in full bridge is times two, like something like this. Now, I think its frequency is twice that of the supply frequency. You can see it. There is something I want to talk about. Wait, let me just stop here. I think it's 30 minutes.